So first we're gonna go over the hypothesis, then this supporting paper, as well as its results, and finally the future direction that can go from this paper. So in the context of flow matching, there were two flow paths were chosen in the papers, which are Gaussian flow path and optimal transport flow path. So for the Gaussian flow path, that's precisely a diffusion model, conventional diffusion models. And we came up with the hypothesis, since the flow paths are predetermined, it directly affects the generative results, would learning a optimal flow path give us, a better result? And this paper directly supports the claim hypothesis. It confirms that like a learnable trajectory is beneficial, and it also learning the optimal forward flow path, optimal forward process would lead to a simpler reverse process. And this generalized other flow matching diffusion framework as well. So let's dive in. So first we'll go over the results and then its flexibility and applications in different contexts. So for the mid-scale image benchmark, we can see that score flow and flow matching is up here. And we have our new framework, neural flow diffusion model with the best result in this paper. And also, this also bring one with flexibility. This can also have bring a few benefits, like one mentioned here. Was if we do the optimal transport case, we see that it requires a lower number of generative steps required for sampling, which is good in some way. And then now we're going to talk about the benefits of flexibility. So here we have the optimal transport loss functions for this case, and we're minimizing the kinetic energies. And this L would be the classic usual loss of neural flow diffusion models. And with this flexibility of adding any loss you want, you can adjust accordingly to any problems that you have, and by simply adding more loss term. And that allows us to incorporate context for any of the problems we have. So next, another possibility would to use this as a bridging model. So we define the target distribution as well as the starting distributions, and see if we can flow from one distribution to the others. And here, looking at the result, it would also bring a very good result benchmark here with an FBM having only 12.6 FID score. And as mentioned before, this is the images for having flexible loss functions. So we can define the loss landscape by just adding more stuff to penalize when the path enters certain regions. Yeah, and that's it for the result of the paper. The math are based on stochastic diffusion models, which are very annoying, but whatever. So this paper provided end-to-end framework for like any flow models, but it also has some disadvantage of having, because we have more work to do, and it has a slower training time. So improvement of these papers, first we can combine with other paths for improvements. So currently the forward process is learned from scratch, and we want to incorporate other information that we already have. That's like we can incorporate optimal transport flow path for the forward process. And, we learn more from it by adjusting accordingly, and that might give us better results and less training hassle. Then second of all, the current paper tested only on like mid-scale dimension image benchmark. So next step is going to apply to more complex domains like high resolution image or video diffusions. And this would test the scalability of learning a noise schedule of the reverse. So basically learning the reverse process. And this can be interesting Yeah, so that's it for this paper. Thank you.